All right, so last class, the last thing that we were talking about was the common ion effect and how that affects solubility. So if we have an ion that's already in solution, and we try to dissolve something that has that ion in it, that ion being present in solution is going to restrict its ability to dissolve into the solution. For example, let's say that we've got sodium chloride. Sodium chloride is very soluble in water, but let's just say that we're trying to dissolve salt, table salt, in water, and it's already got a high chloride concentration. We're adding in sodium chloride, so we're increasing the amount of sodium chloride. There's going to be an equilibrium between these two sides. If we already have a massive amount of chloride in the water, then for our Le Chatelier's principal idea, right, we've already got stuff on the right that's shifting the balance a little bit to the left. Since we wouldn't have any sodium in this situation, we're still going to have it proceed to the right, but this chloride in our Kc or Keq, whatever we want to think about it as, we already have some number for this chloride right, that chloride is already a big number. That's going to make our Kc larger just right from the get-go. So if we wanted to use our reaction quotient and assess how far it was going to move or what direction it was going to move, that would play into it. Another thing that affects our solubility is pH. So pH can affect solubility as well as common ion effect. One example being magnesium hydroxide. If we are in a high pH environment, we're trying to dissolve magnesium hydroxide, so the common ion effect is going to restrict our ability to dissolve magnesium hydroxide. Because hydroxide is already in solution, probably in relatively high amounts. On the other hand, if we move to low pH, we have lots of H+ that will remove hydroxide from solution. And so that's going to continuously pull hydroxide out of solution and shift our equilibrium to the right. So the magnesium will continue dissolving into solution. We would probably end up with quite an excess of magnesium compared to our hydroxide. Generally, our solubility for an ionic compound with a strongly basic or weakly basic anion increases with increasing acidity. So the more acidic, the lower the pH, the more that basic component is going to dissolve. Because the bases react with acid and continue driving dissolution. Or dissolving. 3 of our common basic anions would be hydroxide, that's going to be strongly basic. And then weakly basic, we've got sulfide and carbonate. we see effects of this property. Since rainwater is naturally acidic, it's got dissolved CO2. It might also have sulfuric acid dissolved into it in the case of acid rain. And so it can dissolve limestone calcium carbonate as it flows through groundwater, and then if it comes along an underground cavern, that's when you get stalagmites and stalactites forming because of this calcium carbonate buildup. It's basically just hard water buildup over a really long time and continuously. Which of these compounds, iron 2 carbonate or lead 3 bromide, is more soluble in acid than in base, and why? So what we want to be doing for this question, look at ions that are going to form if those dissolve into solution. We're specifically asking about dissolving in acid, being more soluble in acid, and so we're looking for something that would react with the acid to get pulled out of solution, to drive it into solution. So we're looking for something that's basic for one of our ions. Which of these two compounds has a basic, strongly or weakly, ion in it? It might help to think of pairing things up, right? So we know that the conjugate base of a weak acid is going to be weakly basic. Do either of these have a conjugate base of a weak acid? Yes. It is not PBBr3, sorry. But thank you for guessing. So in this case, it is the iron 2 carbonate. So iron 2 carbonate is more soluble in acid than base. CO3 2 minus is the conjugate base of a weak acid. The weak diprotic acid H2CO3 and it's actually the conjugate base of the weaker HCO3 minus. So that's going to make it basic. If we look at our other negatively charged ion and make that into an acid, HBr, HBr is a strong acid. Since HBr is a strong acid, Br minus is pH neutral. So we've sort of just, surprise, pulled out some ideas that we were talking about chapter ago. Questions? Common ion effect or pH effect on solubility? Okay, getting on to some stuff that's more related to the labs that we're doing this week and next week. Precipitation. You may remember, hopefully you remember, that precipitation is the formation of a solid from aqueous solution. from mixing two aqueous solutions. That's roughly the definition that I give my 3A students. And up until now, we've kind of just done double replacement reactions, and you would have looked at a solubility table and seen, okay, this is soluble or it's not soluble. But we have tools where we can look at extent of solubility. So there are some situations where things that aren't very soluble will still dissolve. They won't form or precipitate. And there are other situations where they will form and precipitate, and we have the tools now to look at that. So for a dissolution, solubility product constant sort of situation, we've got calcium fluoride dissolving to form calcium ion and two fluorides. If we are at equilibrium, then the product of these two, our constant, is KSP. But this only works if we are at equilibrium. So if we're at equilibrium, then the concentration of the calcium ion times the concentration of the fluoride squared is the KSP, but only at equilibrium. At any other point, and also at equilibrium, we can also describe it with the term Q, our reaction quotient, which we've seen before. So it's important to use this Q to let us know, to remind us that it's not necessarily at equilibrium. We're just checking on the state of the system. If our Q is less than the KSP, that means we have less of these dissolved ions than we do at equilibrium. And so the solution is unsaturated. There's more room to dissolve solution. So we've got less dissolved than at equilibrium, and that's why the number is smaller. If Q equals KSP, then the solution is saturated. So we're at our solubility limit, our normal solubility limit at least. If our Q is greater than KSP, the solution is supersaturated, and our solid will precipitate out. If we want to think of this in terms of the balance between our solid and our dissolved ions, if we've got an excess of our aqueous components, that's going to force this equilibrium to the left, and so we're going to reform some of this solid. These Qs are kind of working in the same way that we've seen them work before, where if the Q is less than the KSP, that means that we've got more on the reactant side than we do have on the product side compared to our equilibrium state, and so it can move to the right. We're just describing it in slightly different terms, and our equilibrium expression is a little simpler. Questions about any of those? So we can use Q to predict whether precipitation will occur. So we'll calculate Q and compare to KSP for precipitation problems. Fortunately for us, we don't really have to learn any new math tricks. So we've got a potential precipitation situation, a solution containing lead-2 nitrate is mixed with one containing sodium bromide. The solution is 0.600 molar in lead-2 nitrate. and 0.0158 molar in sodium bromide. And we want to know if a precipitate will form. We should start this by writing out a KSP expression for our product lead to bromide. There might also be instances where you would have to write out KSP equations, balances for both of the possible products, since we've got a double displacement reaction here. For this one, we only need to do the one. So the KSP is for the dissolution of lead 2 bromide to form lead 2 plus dissolved plus 2 Br minus also dissolved. That would be where we get our KSP from. So based on that dissolution balanced equation, our KSP is the concentration of the lead times the concentration of the bromide squared. That squared again coming from our coefficient of 2. Then we can check. What are we checking? What are we comparing? There's something we can calculate. It's a letter. Q. We can calculate Q. So Q is going to be the same as KSP in terms of what it looks like. It's just that it works at any concentration state, any reaction progress state. So this is not necessarily at equilibrium. And we plug in our concentration of our lead 2 plus from our lead 2 nitrate. We've got one lead in lead 2 nitrate, so the concentration is going to be the same. It's going to be that 0.0600, which I read off incorrectly before, times the concentration of our bromide. We get 1 bromide out of sodium bromide. And that is going to be squared. So that gets put into our calculator. Help if I put it in correctly. So I'm getting a value of Q of 1.4978 times 10 to the negative 5. So looking at our KSP and our Q, are they the same? Is one bigger? Q is bigger. What does a bigger Q mean?
Saturated.
Yeah, our solution is supersaturated. The bigger the number, the more the balance is favoring the reactant, or sorry, the product side. So we've got too much dissolved based on our Q value. So precipitate is likely to form. We are going to say that precipitate will form. I was getting all set up for doing an ice table, and then I realized we didn't need to do an ice table. Isn't that nice?
So if from the origin of PV was 2, then would you multiply the 0.06 by 2 in the Q expression?
Yeah, so if we had a subscript of 2 for this,
Mm-hmm.
or wait, is that what you're talking about?
Mm-hmm.
Yeah, so if we have a subscript of 2 here, then each of these, this whole thing, right, the concentration is going to be this 0.0600. But if we dissolve this lead-2 nitrate, or the lead nitrate, and there's 2 leads in there, then we double that concentration.
So you get the original molar amounts from the 2 original solutions, right? Then you plug it in the Q expression, I guess. The concentration is
I think you have the right idea, yes. So let's say that we had, as an example, let's say that we had calcium bromide instead. And it's 0.0158 molar calcium bromide. In solution, right, that's going to be calcium plus 2Br minus. We can do, you can either just see that there's a 2 and multiply it by 2, or we can formally do the stoichiometry step. Or, calcium bromide, we get 2 bromides out for every calcium bromide that dissolves into solution. So it would be 0.0316 molar Br minus in that case.
And if there was one in the NaBr, I guess, if it was Br2, would you include it in the KSP expression or no? Would you put like 2 Br to the power of 2? Is that only for the Q expression?
We're already including that by calculating the concentration of the bromide.
Okay.
So we wouldn't need a 2 in our KSP. We wouldn't put in like 2 concentration bromide squared. Yeah. Other questions about precipitation? We can also do something more interesting. We've already been doing this. Selective precipitation. So there are instances where you may want to remove particular ions from solution. And selective precipitation is the process of pulling out only the ions that you want to from a solution. We're doing this in lab with our qualitative analysis scheme. This also happens if you have a water softener in your house or like on your shower head or something like that. The compounds that they put in there are selectively designed, they're chosen to pull out hard water deposit causing ions. So it's selective precipitation, it's just that you're not really selecting it, somebody else has selected it and you've just bought their product. So we can choose to dissolve, form, or precipitate from any of several dissolved cations, but other ions in the solution. And our qual scheme is already based on that. So we would choose a reagent based on KSP values. We would want low KSP for ions we want to precipitate. So potentially you might spend a lot of time looking at, if you've got a lot of ions, you might be kind of like doing a matrix of like lots of different KSP values. You'd want a difference in KSP values of at least a factor of 10 to the 3. So you've got about 1,000-fold, potentially less, potentially more, depending on the stoichiometry, difference between your solubilities. And then the concentration that we need to actually cause that precipitation, to pull that ion out of solution, we would have to compare our Q and our KSP values. So the lower the KSP is, the less that you would need to add in to actually pull it out of solution. Let's look at a table. This is a table with selected solubility product constants. So this isn't all of them. There's many, many more, I'm sure. We have a solution that contains equal concentrations of barium 2+, lead 2+, and calcium 2+ ions. When potassium sulfate is added to this solution, say we're adding it grain by grain or drop by drop, which of the cations, barium, lead, or calcium, is going to precipitate first? Take a second to scan over the table. So the things that we're looking at, we're adding potassium sulfate. We're adding K2SO4, so we're going to be adding potassium ions. We're also going to be adding sulfate ions. And we're looking for things that will pair up with barium, lead, and calcium. That's going to be the sulfate, since the sulfate is negatively charged. So we're looking at barium sulfate. We're looking at calcium sulfate. And we're also looking at lead 2 sulfate. Specifically, we're looking at KSP values for them. So which of those three compounds is least soluble? Yeah, the barium sulfate is the least soluble. Barium sulfate has the lowest, smallest KSP. And the lowest solubility. It precipitates first. If we had ions that weren't all the same charge, then the stoichiometry might start to come into play, and we might need to actually do some calculations. Since these are all 2+ ions, it's all going to be just that ion paired with sulfate. So there's not going to be like a 2:3 or a 3:2 ratio between them. So our KSP and our molar solubility are going to correlate's not exactly the right word. They're going to be proportional. And we looked at KSP a little bit last class, so reusing that idea. Let's say we've got magnesium and calcium, some common ions, present in solution. They can be separated by selective precipitation with potassium hydroxide. What is the minimum hydroxide concentration that we need to trigger precipitation of our magnesium ion? And we've got our KSP values provided for us. So for our magnesium and for our calcium, we've got our KSP values. What conditions are we going to start precipitating? What causes precipitation in terms of things that we can measure?
Heat.
Did you say P?
Heat.
Heat?
Yeah. Or
that could cause precipitation. That's not what we're thinking about here, though. If we cooled the solution down, that would reduce the solubility. Let's assume that it's constant temperature. Something related to the KSPs. What does it mean when we are at the KSP? It's at equilibrium. There's another thing that's true when we're at equilibrium. KSP and Q are equal, which means the solution is saturated. So if we go a little bit above that, we go a little bit above our KSP, so our Q is slightly larger than our KSP, that's when we'll start to see precipitation. So we're looking for that limit. We're looking for when are we at our KSP. So how much, this is the question that we're answering here, how much hydroxide do we need to reach the KSP of magnesium hydroxide? Because when we're at that KSP, that's the maximum amount that we can have in the solution. If we add a little bit more, if we think about where we get our KSP from, it's going to be from this balanced equilibrium expression. So we're adding in hydroxide until we reach that KSP. When we add a little bit more of that hydroxide, suddenly we're tipping the scale and shifting from the right to the left. At equilibrium, both sides are equal. The rates in both directions are the same. Once we have a little bit excess on our product, that's going to shift it back into the magnesium hydroxide solid. So arguably, the hardest part about this problem is figuring out what are we actually looking for. The math, I think, is not particularly challenging. So we're looking for reaching the KSP of the magnesium hydroxide. We need a KSP expression. Our KSP, we're given the number, right? What's the actual calculation part of it? Yeah, so it's the product side. So magnesium 2 plus concentration, and what else? Yeah, hydroxide concentration squared. And we are given a magnesium concentration, about 0.025 molar. So if we plug in numbers, I know that people often like to look at numbers rather than just doing the pure maths way, and it would look like this. So plugging in everything we know into our KSP expression, we only have one unknown. We've got one equation, perfect. We can solve for the hydroxide. So skipping some steps, we get this. I am getting 2.9 times 10 to the minus 6 molar. All right, if we want to expand on that, we can. We've got a solution with lead 2+ and silver. If selective precipitation is to be achieved using NaCl sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? So not telling you which one precipitates first. And what is the concentration of each ion left at the point where the second ion begins to precipitate? Assuming that precipitation occurs. So looking at numbers, let's work on answering A first. We want the minimum concentration of sodium chloride to begin to precipitate one of the ions, whichever one precipitates first. So we have to ask ourselves which one of these ions is going to precipitate first. Silver chloride has the smaller KSP. It's probably going to precipitate first. If we really wanted to check, we could do the calculation for both of these. The reason we might want to do the calculation for both of them is because it's not an especially difficult calculation. It takes a little bit of time to set up. But we have a subscript of 2 for our lead 2 chloride. So maybe that plays into things. It's probably not going to, but let's just go ahead and go through it anyway. So for lead 2 chloride, PbCl2, our expression is that that's going to be 2+, lead 2+, in solution plus 2Cl minus. Our KSP, lead 2+ concentration times concentration of Cl minus squared. And for silver chloride, we've got AgCl in equilibrium with the silver ion plus 1 chloride. So our KSP is concentration of the products. Skipping a couple of steps to solve these for chloride. They'd look like this. And if you're good at mental math, and you can just do it in your head real quick to check that you don't need to do it, you're welcome to do that. You don't necessarily have to write out that you checked it every single time. If it's a short answer, might be worth doing anyway. Okay, so for the chloride, the concentration of chloride is going to be the KSP 1.17 E minus 5 divided by our lead concentration. Relatively large number. For the chloride, 1.77 E negative 10 divided by 0.025 molar, which is a much smaller number. This is 7.08, sorry, times 10 to the minus 9 molar. So looking at these two, right, we can tell our prediction was correct. The silver chloride is going to precipitate out first. It needs a very small concentration compared to our chloride. Conveniently, because we've got this second part, we actually didn't waste any time doing the chloride concentration for lead 2 chloride. That'll come into play for part B. So for A, our answer is 7.08 times 10 to the minus 9, or 7.1 times 10 to the minus 9 molar. Our silver chloride starts to precipitate out. So it does precipitate out first like we predicted. And then in B, part B, what's the concentration of each ion left at the point where the second ion begins to precipitate? So we've already calculated where our second ion begins to precipitate. That's for the lead 2 chloride, the 0.0117 molar. So our PbCl2 starts to precipitate. At that concentration. Up until the point that we reach that concentration, is any of our lead going to precipitate out of solution? If we have less than this concentration of chloride, will any of our lead precipitate out of solution? It won't. Our Q will be lower than our KSP. Right, so this chloride concentration is telling us when we hit this, that's when we're saturated. If we go above this, we're supersaturated. If we're below that, then we're not saturated. So right at the point when we hit this, we've reached our solubility limit. None of our lead is going to precipitate out yet. So the concentration of lead that we have at this point is still 0.085 molar. We're at the limit, but not over. This is for answering part B. So our lead 2 plus concentration, 0.085 molar. So there's not really a calculation for that one. It's just conceptually identifying what's happening at that limit, or what's true or what's not at that limit. We do have a calculation for our silver chloride, though. So we are now at the point where our second ion begins to precipitate, the 0.0117 molar. That's way above the amount that we need for our silver to start precipitating. In reality, our Q is only going to get as high as the KSP. If it goes above, then stuff will start to precipitate out. If we keep adding in chloride, silver is going to continuously precipitate out to compensate so that the KSP or the Q stays at the KSP value. So for B, for silver chloride, we want to find the silver concentration when chloride concentration equals 0.0117 ... molar. So we will get concentration of silver equals KSP over chloride. And I'm not going to write any of the numbers in because I have backed myself into a corner. So our silver concentration, 1.51 times 10 to the minus 8 molar. That would be our silver concentration when the second ion begins to precipitate. Questions about any of the steps?
Would this be a short answer question?
This could certainly be a short answer question. Thank you, that's a great idea. Part of the reason I gave 6 points per question on this last exam, because there were only 4 questions, and if I give you more points per question, that's more points that I can give you for partial credit. So like this one has many parts to it. It's kind of a two-parter, so I might give 3 and 3 or 4 and 4 or something, and then just showing that you're thinking about Q might score you some points. Figuring out part of it might score you some points. This would be maybe a bit of a nasty multiple choice question. It's a lot of work for 2 points. So where this comes into play, the selective precipitation, is for qualitative chemical analysis, or what I've been calling qual scheme. This is the qual anal in the course description. So we kind of have to cover it. It's in the name. So we are concerned with finding the kind of ions present in a solution. It's qualitative. We're looking at qualities of the solution. So looking at qualities. Like type of ion. Other examples of qualities, things like color, smell, etc. For quantitative analysis, quantitative looks at quantities. Amounts of chemicals. And quantitative analysis is, if we were pairing it with the same qual scheme that we're doing, would be quite a chore. Because not only would you have to separate out all of the ions, we would have to identify, or might actually be easier to separate them, but you'd be looking at how much of each ion do you have, and so we would be making up lots and lots of solutions, dilutions and whatnot in lab.
the smell?
For our qualitative analysis, we would not be using smell or color probably. The color is helpful, but we're really just breaking down like with a no numbers approach, like what's in it. If we were doing fruit research, then smell, taste, color, feel could come into play. So at the nearby USDA lab, there are people that are doing research on different varieties of fruit and comparing, like, okay, how does this new avocado variety compare to the Hass avocado that's pretty dominant on the market? And so they get a taste panel, bunch of people to come in and like taste different things, and like they're looking for, you know, how buttery is it, how fruity is it, how smooth is it, doing qualitative analysis that way. And then they might also do quantitative analysis, like, okay, what are the actual like oil contents in the avocado, or, you know, what things are present. They might do, there is actually a machine that's used for smelling individual components in a mixture. So you separate out all the components, and then somebody gets to stand at a little nose piece and just smell for however long the run is. Just the driest air that you've ever smelled. And then all of the individual components that come out, whether they're good or bad, they get to smell them and mark like the time and, okay, what was the aroma, and then try to correlate those with things that they know are in the solution. So we're not doing those quality tests, but there is a time and place for those. For our qualitative chemical analysis, we've got a mixture of metal cations, and we separate them out with several precipitating agents. So things that will catch a group of ions. So initially we start off with a mixture of, we're just calling them A, B, and C cations. We add a precipitating agent, something that will pull several of those cations out. So cation A then shows up as a solid, and we can pretty easily separate a solid and a liquid, especially if we're not, you know, doing quantitative analysis. We're just looking at the qualities. We can separate it out by centrifuging it. So all the solids go to the bottom. We keep the liquids. We just pour the liquids off. We don't even have to do a nice filtration. Then we've got fewer liquids in there. We can add a different precipitating agent. We catch cation B then as a solid, and now only cation C is in solution. We pour the liquid off, and now we've separated out those three cations. So this is exactly the stuff that we're doing in lab this week, and we'll be doing more next week. This is a little bit simpler. So what we're doing in lab is multi-step. So we're separating out batches of things, and then in each of those batches, we're pulling out individual ions one at a time. Fortunately, arguably the hard work has been done of putting together the qualitative analysis scheme, because like this is one possible scheme that you might have. So this is an example of what a qual scheme flowchart might look like. So initially, we would be testing, looking for all of these possible initial cations. And if we were working in a commercial lab, then it might be, like these might be all of the ions that we offer customers that we can look at. We might say, you know, put a cost on each of these groups. Say, if you want us to look at each of these groups, we can do that for you. It's going to cost so many dollars to do each of those. If you'd like the full thing, that's the most expensive. If you just want us to look at a few, we can do that too. So the most robust separation, we might precipitate out are insoluble chlorides, things that have very low solubility limits. If we add hydrochloric acid, the chloride of the hydrochloric acid is going to pull out these insoluble chlorides. So these have low KSP, and they have chloride in them. So that step pulls that out. Then our remaining cations, we can add H2S to pull out our acid-insoluble sulfides. So these are things that have a low KSP with S2 minus. So they'll readily pair and form a solid with S2 minus. They have a very low solubility limit. If we add just a little bit in, it starts to precipitate out. Then we can decant, so pull this precipitate off. The remaining cations, we then add hydroxide to get us up to a pH of 8, and this pulls out a bunch of different things. So we've got hydroxides and base-insoluble sulfides. So we might have sulfides that dissolve in acidic solution. We had acid previously. If we change it to a basic solution, then that can pull out some of these other things as well. And then adding in ammonium hydrogen phosphate, we can pull out insoluble phosphates, and then only the things that we can't really remove are left in solution, alkali metals and ammonium. There's also a certain amount of care that comes into picking, like you can't just use kind of whatever you want that's got hydrogen phosphate here. If we used something that had a metal cation on the front, then that would add metal cation to our solution, and that would be a problem. So for all of these, we've just got hydrogen, or in the case of this last one, ammonium, because we can't really check ammonium, probably. So a bunch of steps. So looking at the different groups. For this particular qualitative analysis scheme, we've got insoluble chlorides. Most chlorides are soluble, but silver, lead 2 plus, and Hg22 plus all have very low KSP when they're paired with the chloride ion. So those will come out of solution very easily. This is a great first step since most chlorides are soluble. If you were working in a lab, you would also have this would be kind of a set procedure. You would just run through all the steps. So I don't expect you to have memorized these steps. I think that would be a big waste of time, having you memorize the steps. Understanding why we do the steps is more important, and this would also make for a thriller of a short answer question. Give you a qual scheme and ask you to describe the steps that you would take to separate those ions. That'd be so fun, wouldn't it? We also have our group 2. So after we've pulled out our chlorides, then we can add in H2S. H2S is a weak diprotic acid, and our concentration of S2 minus is pH dependent, since we've got H plus on the product side of each of these. If we've got an acidic solution, we're going to have a high concentration of H plus, so we'll mostly have HS minus or even H2S. So we won't have much of this S2 minus in the solution. This is kind of already written out, but the S2 minus concentration is very low. At high concentration of H plus when it's acidic. So since we acidified our solution in the first step, adding in H2S means that we'll have a very small concentration of S2 minus. Only the things that are very insoluble with S2 minus are going to precipitate. So these are the things with the lowest KSP with S2 minus. weird. They precipitate at low S2 minus levels. So we're keeping our sulfate level low, or sulfide level low. And we get to pull out solids. There are other things that have higher KSPs, still relatively low, so they can precipitate out with S2 minus, but they need a higher concentration of S2 minus. So that's where the base insoluble sulfides come in. Additional base is added. When hydroxide is added, S2 minus concentration increases because this H2S equilibrium bit gets shifted. So we're decreasing our concentration of H plus for both of these, and that will cause a shift to the right. So our sulfide concentration increases. We're pulling H plus out, increasing the solubility. We talked about this sort of concept earlier, pH-dependent solubility. So pulling out H plus, that's going to cause more HS minus to dissolve. If we keep alkalizing, but if we keep increasing the pH, more of that H plus comes out of solution. We can drive more S2 minus into solution. And so we can pull out things as sulfides. These are more soluble with S2 minus than previous step, or previous group. But the increased concentration of sulfide causes them to precipitate. So just kind of explaining what's going on there. And we also have things that will precipitate out as hydroxides. Because now we don't have an acid-dominated solution, we've got a base-dominated solution. And so these can precipitate. Again, it's all about the KSP of the particular compounds. So those would all come out as solids. We decant and continue pulling out more ions in our group 4. And our group 4 is our insoluble phosphates question.
So can you go back up? So when you add more H2S, does that make the H plus ion go down the pH? Or what does the arrow down mean?
These arrows?
Yeah.
Those are dropping because of the additional base.
Oh, okay. That's what I'm saying.
Just showing the Le Chatelier's principal stuff going on. So our phosphates can be removed, or our insoluble phosphates can be removed, it's going to be alkali and alkaline earth metals that are left over. And we can remove our alkaline earth metals, our group 2A metals, by adding ammonium phosphate. Since that's pretty much all that should be left at this point, at least for the ions that we're targeting. And then our most soluble metal ions are the alkali metals. So lithium, sodium, potassium could all still be in there. More than likely, it would just be sodium, potassium. And those cannot be precipitated. So we would do a flame test. So we'd put the solution into a flame. Metals in high enough concentration burn. And the color changes for the color identifies the metal. In this case, our sodium is going to burn with this reddish flame, and our potassium is more of a purpley. There's a particular shade of blue that's coming to mind, but I can't remember the name. But more of a bluey flame. And we don't do this in our qual scheme because you have to have enough in solution for it to burn and like change the color of the flame. And it only burns for a really short amount of time. So apparently what used to happen, you take a little piece of wire and you dip it into your solution, you put it in the flame, you dip it in your solution, you put it in the flame. You'd have to do it over and over and over because it burns up really quick. So it just wasn't very satisfying. You had to have a lot in there. In these pictures, it looks like they've got a little syringe that they're using to add solution in continuously, which would probably work a little bit better. Another way to do it would be to maybe concentrate it a bit so that you've got more of the ion per amount of solution. That might give you better results. But that's part of why we don't do flame tests.
So Na, K, and ammonia will never be a precipitate for them? Or only for this?
I don't know that they'll never be a precipitate, but it's probably very difficult. I'm guessing that if you can get them to precipitate out, it's not worth doing it another way. Like it might be more expensive, or it's like more dangerous or difficult to clean up, whereas this is basically free. Questions about our qualitative analysis?
So you can test sodium and potassium, but what about NH4? You can.
Ammonium might be one that you can actually just smell it, but the issue is, right, in this group 4 for our insoluble phosphates, we added ammonium phosphate, and that's actually, there's supposed to be a hydrogen there, I think. So because we added in ammonium, that kind of confounds things. So we just wouldn't be looking at ammonium. But you might be able to smell it before you add this ammonium phosphate if there's some ammonia in there, or ammonium. All right, more fun stuff. So our transition metal ions, stuff in that nasty block in the middle between scandium and zinc are often good Lewis acids, meaning that they're electron acceptors. Lewis acids was the last definition of acids that we learned. Water molecules, because of the double lone pairs on oxygen, these lone pairs can donate to these Lewis acids, so they can act as Lewis bases to hydrate, adding water onto the transition metal ions. So in solution, silver ions are hydrated. They pick up 2 waters. In reality, our silver ion doesn't exist as a bare ion. Similar to how our H plus doesn't exist as H plus in solution, it's actually hydronium H3O plus. A complex ion, as opposed to a simple ion, or a complex as in like multiple things together, like a gaming complex or a sports complex or a housing complex, right? Central atom with 1 or more ligands. Ligands basically just means groups, things that are attached. I think it actually has to do with sticking, like it's the same base word, I think, as colligative, sticking together. Ligate, I think is the word. I'm pretty sure it's Latin. Not that any of that matters. So a ligand, in this context, is a neutral molecular ion that acts as a Lewis base with a central metal ion. So it's donating some electrons to kind of stick to the metal ion. Right, so it might look something like this. We've got the waters coming up next to it, kind of sort of donating their electrons a little bit, maybe forming an adduct, who knows. We can swap ligands. If we add a stronger Lewis base, something that's better or more willing, more ready to donate electrons, then it can displace the water. Because in solution, well, in anywhere really, all of our atoms and molecules are kind of buzzing, bouncing around. And so it's entirely possible that one of those waters would pop off briefly. And if there's something stronger, it'll pop on. And it might not pop off as readily. So it'll get stuck, and then it's hard to remove. You can think of it as like different strengths of tape. One of them Scotch tape, the other is like Gorilla tape. If you're constantly sticking and unsticking, the Scotch tape is probably going to come off pretty easily. The Gorilla tape might take you 3 times as long, 4 times as long to pull it off compared to the Scotch tape. So eventually it's just Gorilla tape. So these stronger Lewis bases stick to the complex, or stick to the transition metal for a longer period of time, or sticks more strongly. And when we are dealing with these complex ion equilibria, we often leave water out of the equation. So we'll show it as Ag+, even though we know that it's actually got some waters on there. So there are secretly waters here. And for this, we get a new equilibrium constant called the formation constant, Kf. So the F stands for formation instead of freezing. So if you add ammonia to a solution with silver, they will get in formation. So we're forming the complex ion between the silver and the ammonia. It's really the same sort of looking thing as we've seen before for a K. And here's a peek at formation constants, Kf values for some selected complex ions. There's a lot of them. You don't need to memorize them. But notice that they're all big numbers, like 10 to the 7, 10 to the 3 are the smallest ones. But we've got as big as 10 to the 43, 10 to the 33. These are all huge K values for what we've been looking at. Questions?
So when it's a strong base, then you don't put water in the expression? Or is it
So for this,
like that? That one?
the secret waters,
Yeah.
that's just for convenience sake. We're leaving the waters off just because it's convenient to not write them.
Okay. So you kind of just leave water off for every expression?
Yes. If we're putting it into a KF, yes, we're going to leave those waters off. Okay, we are in the lab now, finishing up the lecture for this chapter since we are so close to wrapping it up. Okay, so we were just talking about formation constants and that they're very large Q numbers, huge Q numbers, right? Enormous. We can do calculations with these. I know that you're all wondering it. Can we do calculations? Yes, we can do calculations with them, and you're going to love this. So we mix a 125 milliliter sample of a solution that is 0.0117 molar in nickel 2 chloride with a different sample of a solution that has ammonia in it. After the solution reaches equilibrium, what concentration of nickel remains? We've got a K value. We saw 2 slides ago that we can write out a new expression. So our K formation is the complex concentration of the complex ion nasty formula over the things that go into it. So the things that go into it are the nickel 2 plus concentration, and we also have ammonia. How many ammonias do we have? Let's write out the actual equilibrium expression. Probably should have started there. So nickel 2 plus, and we know in our brains there's waters there. We're not showing them, but we know there's waters there. And we're adding something. We're adding ammonia, right? To get this NiNH362 plus complex. How many ammonias do we need? 6. So we've got a delightful 6 in front of this ammonia. So that means that in our KF, our ammonia is raised to the power of 6. Let's look at what happens if we do an ice table the way that we've always done it. I'll do the ice table over on the right since I've already got everything written out. Our initial concentrations, once we've mixed these, we don't know. We have to calculate that, right? So the concentration of the nickel, the concentration of the ammonia, we're mixing 2 samples together. So we get to do some dilution stuff. Our final volume is going to be 300 milliliters, adding up the 125 and the 175. We've got a nice convenient formula for dilution. This one that we only use for dilution, never for anything else, only for dilution. Right, the M1V1 equals M2V2. Our M2, the thing we're looking for, is going to be M1V1 over V2. So for nickel and for ammonia, 125.0 milliliters, that should be the second thing I write. 0.0117 molar and 300 milliliters on the bottom. So the milliliters cancel, we'll be left with units of molarity. We can do the same thing for our ammonia. 0.250 molar times 175.0 milliliters over the final volume of 300 milliliters. The milliliters cancel, we'll be left with units of molarity. Put those into the calculator real quick. For nickel, 4.875 times 10 to the minus 3. I've got my calculator in scientific notation mode from earlier. And for the ammonia, 1.4583 repeating times 10 to the minus 1. And our initial concentration of the complex ion is going to be 0. We haven't formed any of it yet. Our change values, we would have minus x minus 6x because of the 6 coefficient, and plus x, and we would end up with 4.875 times 10 to the minus 3 minus x, 1.4583 repeating times 10 to the minus 1 minus 6x, and x. I would recommend not copying stuff down for this part of the ICE table. Just follow along and watch the madness unfold. Okay, so if we try to do an ICE table, right, this is the ICE table as we've known it, as we've loved it, as we've hated it, as we've grown together, and all that. And our KF expression, if we try to plug it in, we'll have x on top. Okay, didn't want to do that. We'll have x on top. And in the bottom, we'll have this, that minus x, that's a term, times this other term, raised to the 6th power. Does that look like a problem that we can solve? If we do this 1.4583 repeating times 10 to the minus 1 minus 6x to the power of 6, we'll end up with something x to the 6 with probably some x to the 5, 4, 3, 2, 1, and 0. What a horrible nightmare. Can we say that X is small? What's our KF value? Really big, right? 10 to the 8. So that doesn't work. So we're doing something completely different, and that's why I told you to not copy along. So our KF is so large, right? 10 to the 8, absolutely enormous number. So it's almost entirely going to be the complex ion. So we are just going to work off the assumption, since K is massive, absolutely massive, we're going to work on the assumption that all of the nickel turns into the complex ion. Because the amount of nickel that we'll actually have is basically a rounding error off from how big our KF is. So scratch our ice table as we've been using it. Can delete all of this stuff. So our assumption, KF is huge. So approximately all nickel goes to the complex ion. So the value that we have for the nickel, since it's less than the value that we have for the ammonia, even times 6, that's going to be our concentration of nickel. So plus 4.875 times 10 to the minus 3. Our concentration of the complex then, 4.875 times 10 to the minus 3. In order for that to happen, we're getting rid of some of this ammonia, and we've got an excess of ammonia, so it's going to be minus 6 times 4.875 times 10 to the minus 3. And we can calculate that. So our equilibrium concentration of the ammonia should be about 1.16583 repeating times 10 to the minus 1. And our concentration of nickel is going to be X. New wave ice tables. Fingers crossed I'm doing it correctly. Because this is also, it's very different from what we've been doing. So we're looking for our concentration of nickel. Our concentration of the complex ion goes on top. That's what our nickel concentration was. We've got an X down here for our concentration of the nickel. We'll be finding that. And 1.16583 repeating times 10 to the minus 1 to the 6th power. If we solve this for X, we would just be swapping the X and the KF. So that 4.8753 times 10 to the minus 3 divided by our KF, and our KF is multiplied by that other number raised to the 6th power. So X is 9.7 times 10 to the minus 6 molar. So because Kf is so astronomically huge, and we run into big problems if we've got something raised to the 6th power, we're doing a different type of x's, small or big. In this case, the x is our concentration of nickel. Other than this being completely subversive and confusing, any questions?
So why is the X positive on the reactant?
Why is the x positive for the reactant?
Yeah.
Because we can't have a negative amount. So Kf, completely different kind of ball game. We also have solubility effects for complex ion equilibria. Our solubility of an ionic compound containing a metal cation that can form complex ions like the Ag NH32 or whatever it was that we saw earlier, that's also here on this slide, is going to increase. So solubility of this compound, wrong tool, solubility of this compound is going to increase when we've got Lewis bases that can complex with the silver. So silver chloride in solution is going to have a higher solubility if we can pull the silver into something else that's soluble. So AgCl is not very soluble. When our Lewis base is present, it removes Ag plus from the equilibrium. So this AgCl equilibrium. So that drives solubility of our silver chloride. The silver is still dissolved, but because it's complex with ammonia or with a cyanide group or with a hydroxide group, when it's complex with those, it's not able to go back and reform the silver chloride. So it feels to me sort of like cheating a little bit, but it works. This is how it actually happens. And the pictures that we've got here is we've got some silver chloride that's in solution, or that's not in solution. It's a solid just sitting on the bottom of our beaker. If we add in a complex ion, like ammonia, then that causes it to be soluble enough that all of that solid goes into solution. That might be beneficial if we need a lot of silver in solution to do a reaction. I don't know what reaction that would be, but that could be one possible application of this idea. If we want to look at some numbers, our change in solubility is very large. So our KSP was 1.77 times 10 to the minus 10. We saw that previously. Very low solubility. But our KF is a really high number. If we multiply those two values together, that gives us our new K for the overall bit. which is 3 times 10 to the minus 3. So we've improved the solubility by quite a lot. Some might call that massively. And the reason that we're multiplying these is because we've added the equations together. So we're getting the silver plus ion out, removing that to get an overall reaction for the new compound with the complex ion. So it's like we saw on exam 2 for one of the short answers, where we had a couple of k values and you can multiply or divide them to make stuff happen. We're also doing that here. All right. Which compound, when added to water, is most likely to increase the solubility of CuS, copper 2 sulfide? It's not D. What are we looking for? What kind of thing are we looking for in each of these possible options for answers? What's going to increase the solubility? It's something named after a guy. Yeah, the Lewis base. We're looking for a Lewis base since Lewis bases can form complex ions. And increase solubility. We have a list of common Lewis bases. There they are. Ammonia, cyanide, hydroxide. Do we have ammonia, cyanide, or hydroxide? We sure do. We've got cyanide in sodium cyanide. So our cyanide ion can complex with the copper. If you were given a table of Kf values, formation values, then it would be up to you to pick the one that's got the highest Kf value, because that is going to be the one that's got the highest solubility, probably. So that's what we're looking for. We also have amphoteric, meaning they can act as acid and base metal hydroxides. So many of the metal hydroxides are insoluble, they don't dissolve, or they're very slightly soluble in pH neutral water. So if it's around 7, they're not going to dissolve. Metal hydroxides are typically more soluble in acidic solutions. since the acid reacts with the hydroxides, right? So that's going to drive solubility since we're using up one of the things that's dissolving. So that's going to drive solubility. Some metal hydroxides are amphoteric and can also act as acids. So they also have increased solubility in basic solutions. For example, aluminum hydroxide can add another hydroxide onto it. So aluminum hydroxide is soluble at both high and low pH, but not soluble or insoluble at pH neutral solutions. Aluminum, you may remember, has a tendency to form, like if we had just H's here, right? Aluminum would be happy with its Lewis structure. It tends to form Lewis structures that only have 6 electrons on the aluminum, meaning that it has an empty spot to accept a lone pair. So if we apply that same idea, right, this makes it a Lewis acid. Hydroxide is a Lewis base, so the Lewis base can add onto the aluminum hydroxide and pull it into solution. Since it's charged, it's going to have the ion dipole intermolecular forces that will keep it in solution, since water is strongly polar with hydrogen bonding. So aluminum is one that can do that for those reasons. Because hydroxide is a Lewis base. We can also consider a hydrated aluminum ion. Very interesting. So aluminum ion in solution is inherently acidic. It's small and highly charged. This was one of the ones that I think I mentioned that you should memorize. The other one being iron 3+. When it's in water, it's going to be hydrated. It's going to have a bunch of water sitting on it. It can add another H2O, or if we have another H2O in there, one of the waters that's on the aluminum can donate an H+ to form H3O+, and then this whole complex thing. If we add a base that drives the reaction to the right, we're removing these protons. So we're removing these H3O+ when hydroxide is added. And that can happen a couple of times. So one removal, we make some water. Another removal, another hydroxide, we make another water. And eventually we end up with AlH2O3, OH3. And like before, there are secretly waters here. We're omitting them because they're not that important, really. So we end up with that aluminum hydroxide solid that we saw earlier. So this was from the previous slide. And then if we add some more base, it can dissolve that solid. This is, again, just what we saw on the previous slide. And there was a typo here. It's supposed to be a 4. So it picks up another OH. It displaces one of the H2Os on there. And here's a fun image of pH neutral. Our insoluble aluminum hydroxide solid will precipitate out a solution. If you're at low pH, we can form the hexahydrate complex ion that will dissolve into water. If we're at high pH with extra hydroxide in there, then we can form the version that's got 4 hydroxides. So the Lewis base causes it to dissolve into solution. Very fun, very fun. Very good stuff. All right, so some cations that form amphiteric hydroxides include these: aluminum, chromium-3, zinc, lead-2, and tin-2. These are both acidic and basic, or can act as both an acid. Potential. So they'll dissolve in acid, will also dissolve in base. Questions about amphiteric metal hydroxides or formation constants? Great, we are free. We're finally free from aqueous ionic equilibria. We'll start chapter 19 next week.